remind you, you have test corrections due Tuesday. So if they're done and you're ready to hand them in, you can put them in your folder. Otherwise, they're due Tuesday. And the guidelines are all written up here. Don't change the original test. Redo the problems you got wrong, showing all your work, giving explanations as needed. You can earn up to half the missed points for each corrected question and submit it with your original test. Okay, so today we're going to talk about, we're going to start with some activities from lesson 23, so some practice doing the quadratic formula. And then we're going to work on class 24, which is quadratic formula part 2. Okay, so just all today is the quadratic formula. And a reminder that quest 4 is a week from today, the 19th, quest 4. You have your usual preparation methods with your practice problems packet, solutions to it are in Moodle, old homeworks, and you can bring a sheet of notes as usual. Yes?
There won't be anything on there that will be table.
The perfect powers? I don't think so. I don't think you'll need it. Yeah. Although if you don't have the perfect squares memorized, you might want it, because if you're simplifying something with the quadratic formula, yeah, so you can use it if you want.
Okay, yep. So a 1-page of notes and the perfect powers table.
Sure. Yep. And you'll be allowed a calculator for this one. And I wanted to give you a heads up that there is a section where you'll be solving quadratic equations, and you have to use a method other than the quadratic formula. Okay, so you cannot rely solely on the quadratic formula. You have to know the 2 other methods that we learned, factoring and taking the square root of both sides method. All right, so yes, it said, yes, the section says solve the following quadratic equations using any method other than the quadratic formula. Right. Okay, so this is where we left off last class. This is page 179. Most of you were either finished with part A or working through it when we left. So I thought maybe we'd do that together, and then we could do one more if you want before you spend a little time finishing these activities. So if we look at part A, we're going to solve using the quadratic formula. So you have 3x squared minus 4x equals 4. Before you can use the quadratic formula, one side of your equation has to be 0. Okay, before you can identify A, B, and C, one side has to be 0. So what should I do first? Minus 4 from both sides. So I have 3x squared minus 4x minus 4 equals 0. So then I identify my A, B, and C. What is A in this equation? B is -4, and C is -4. Okay, so then the quadratic formula says that if I want to solve this equation for x, x equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. All right, now I just replace my a's, b's, and c's with the numbers using parentheses every time I replace a letter with a number. So negative is part of my formula, so I copy that. And then I put in b, which is -4, plus or minus the square root of b squared, -4 squared, minus 4 times a, which is 3, times c, which is -4, all over 2 times a, which is 3. Okay. Every time I put in a number, I put parentheses around it. That will help me not mess up my negative signs. Okay, -4 is +4. -4 squared, 16. Okay, this part gets people tripped up a little bit. Think of that subtraction sign. We read it as minus when we read the formula, but think of it as a negative sign on the 4 right after it. So that says -4 times 3 times -4. What's a negative times a positive times a negative? Positive 48. Positive 48. And then that's all over 6. So this is 4 plus or minus the square root of 64 all over 6. 64, is that a perfect square? Yeah. Square root of 64 is 8. So this is 4 plus or minus 8 over 6. You can either break it into two fractions here. So you have 4 over 6 plus or minus 8 over 6. Right? Or you can add the numerator, add and subtract the numerators first and then divide by 6. Either way, works the same. Okay, so I'll do it both ways. So we could break this into 4 over 6 plus or minus 8 over 6. Right? So we do the plus first. 4 plus 8 is 12. And when you're adding fractions, the denominator stays the same, right? So we have 12 over 6, or then we do the subtraction. 4 minus 8 is -4 over 6. And 12 over 6, what does that reduce to? 2. 12 over 6 is 2. And -4 over 6 reduces to -2 thirds. You get the same thing if you did the numerators first. You could do 4 plus 8, which is 12 over 6, which is 2. 4 minus 8, -4 over 6 is -2 thirds. What do you think? Should we do one more, or do you want to jump in and try some? Okay. See with the fractions. Okay. Fractions do look scary, right? So when you see them, your first thought should be, let's get rid of them, right? So you get rid of fractions in an equation by multiplying both sides of the equation by the LCD, the least common denominator. So I've got 3 terms, x squared over 6, x, and 2 over 3. Now the x I could think of as x over 1, right? Okay, so what's my least common denominator for 6, 1, and 3? 6. The least common denominator. If I was going to get a common denominator, imagine you were going to add all those fractions together. You've got a denominator of 6, of 1, and of 3. What's your common denominator going to be? 6. I already told you the answer. 6, right? So you're looking for the least common multiple of 6 and 1 and 3, right? A number that will clear all the fractions. You don't know what I'm talking about? Okay. All right, so if I multiply both sides of this equation by 6, let me rewrite it. So first you imagine, like, what if I wanted to add all those fractions together? My common denominator would have to be 6, right? I'd multiply the second fraction, x over 1, by 6 over 6. I'd multiply the third fraction by 2 over 2. So they'd all have the same denominator of 6, right? But instead of actually making them all have the same denominator, I'm going to use that common denominator to get rid of all the denominators. So I'm going to multiply both sides of my equation by 6. And if it helps, you can put a little over 1 here. It helps remind you that that's the numerator of a fraction. Okay, so now I'm going to distribute my 6 to both terms on the left. So I get 6 times x squared over 6 plus 6 times x over 1. And again, if it helps, you can put the over 1s there. And that equals 2/3 times 6. Didn't actually do any of the multiplications yet. I just wrote out what I was multiplying. Okay, 6 over 1 times x squared over 6. You've got a 6 in the numerator, a 6 in the denominator. They cancel. So all that's left is x squared over 1 or just x squared. 6 over 1 times x over 1. What does that simplify to? 6x over 1, which is just 6x. And then 2 over 3 times 6 over 1. You could think of that as 12 over 4 and then reduce it, or you could cancel before you multiply. And 3 goes into 3 once, and it goes into 6 2 times. So that comes out to 4. 2 times 2 is 4. Okay, so now I've made this into a quadratic equation. I need to have one side be 0 before I can use the quadratic formula, so I'm going to subtract 4 from both sides. Okay, what's A, B, and C here? Yep. Great. A is 1, B is 6, C is -4. So I just plug those numbers into the quadratic equation. Okay, and every time I put in a number instead of a letter, put parentheses around it. So that negative sign is part of the formula. I always copy it. Put in a 6 for B. -6 squared minus 4 times A times C all over 2A. Okay, -6 squared is 36. And then I have -4 times -4, which is positive 16. So that's 36 plus 16, which is, 46 plus 6 is 52 all over 2. Okay, is 52 a perfect square? Nope. Does it have any factors that are perfect squares? Any numbers that go divide into 52 that are perfect squares? Definitely 4. Does it have any bigger ones? So you can just pull out a calculator and check them, right? So we've got 52 divided by 4. That's the first perfect square. The result is 13, which means that doesn't have any bigger ones because 13 is prime, right? But even if you didn't recognize that, you could just keep checking. You go, well, what about if I divide by 9? Nope, that doesn't work. What if I divide by 16? Nope. What if I divide by 25? Nope. 52 divided by 36? Nope. And 52 divided by 49? No. And then my squares are bigger than 52, so it's not going to work. Okay, so 4 is the only perfect square factor for 52. So I have -6 plus or minus the square root of 4 times 13 all over 2. So I just rewrote 52 as 4 times 13. And then you can take the square root of 4. What's the square root of 4? 2. So once you take the square root of 4, you write the answer outside of the radical because you just took the square root. So it no longer belongs underneath there. So we have -6 plus or minus 2 square roots of 13 over 2. Break it into 2 fractions and reduce it. So this is -6 over 2 plus or minus 2 root 13 over 2. -6 over 2 reduces to -3. And these 2 over 2's cancel. So I have plus or minus square root 13. That was a good one to go over because it had the fractions and simplifying a radical. It wasn't a perfect square. Mm-hmm. Oh, okay. So our approximate values means type this into your so this is an exact answer. Okay, so any square root that isn't of a perfect square number is what we call irrational. And when you try to take the square root of, say, 13, it gives you an infinite decimal that goes on forever and ever and ever with no repeating pattern, like pi, right? So square root 13 is an irrational number. So as soon as you try to convert it to a decimal, if you ever stop writing decimal places, you have rounded it. So that's why we say it's an approximate answer. So we have the calculator do this, do 13. My calculator is a little less convenient than yours. I have to do the square root first, then add -3. So I get 0.6055, approximately 0.6055, or now I have to do the minus. Okay, so I have -3 minus, I meant to hit -3, 3 negative minus square root of 13. I get -6.6055. So those are your approximate answers. Maybe. Yeah. It's possible. Okay. So from class 22 homework, this was the first one. You're right. You're supposed to graph this equation, this parabola on graph paper using the 6-step process. So whatever you figure out, you know, you've got a bunch of points, you plot it, and you're not sure if you did it right because my math lab isn't giving you the answer, right? So here is a way that you can graph it and see what it actually looks like. So I open up Geogebra. Okay, so it's just a graphing program. In the input bar at the bottom, you just exactly type the equation that was given to you. So I type y equals, to square things, you use the little caret. It's like a little pointy hat that's over the number 6. So you do shift 6. Oops, I forgot x squared minus 8x plus 12. You hit enter, and it graphs your parabola. And then if you need to change the scale or move things around, you click this little movie button, the arrows, and it moves things around and you can change the scale. So, but that will give you a good idea whether or not your graph is correct. So you can use that when you're checking your homework. All right, so moving on to lesson 24. We're going to see how we can use just a piece of the quadratic formula to determine the nature of the roots of a quadratic equation. And we're going to discover a brand new set of numbers called the complex numbers. Okay, so in our last lesson, we graphed this equation y equals x squared minus 4x plus 5. We saw that it doesn't touch the x-axis ever. But what happens if we were to use the quadratic formula anyway, right? So if it doesn't touch the x-axis, that means there are no real solutions to this equation. But let's see what happens if I use the quadratic formula anyway. What is A, B, and C for this equation? Yep. Yeah, and 5. Good. Okay, so my quadratic equation, x equals -b plus or minus the square root of b squared minus 4ac all over 2a. Put in all my numbers, so I have -4 plus or minus the square root of -4 squared minus 4 times a times c all over 2a. So every time I replace a letter with a number, you use parentheses so you don't mess up your negatives. Negative 4 becomes 4. Square root. Negative 4 squared, that's 16, minus, I have negative 4 times positive 1 times positive 5, right? So negative times a positive comes out to negative, and it's negative 20. So I have minus 20 all over 2 times 1 is 2. So this is negative 4 plus or minus 16 minus 20 is negative 4 all over 2. So I try to do the quadratic formula and I end up with a negative under a square root, which up until this very moment in your whole life, you've always said you can't do that, right? You can't take the square root of a negative. There's no number that I could square and get a negative 4 as the answer, right? So I might try negative 2, right? It's not 2 because 2 squared is 4. Negative 2, but that doesn't work either because negative 2 times negative 2 is also positive 4. So we know from our earlier work, simplifying square roots, the square root of a negative number is not a real number. There are no numbers that we know of that you can square and get negative 4. Yeah. Oh, sorry, that should be, you're right, that's a typo. It's just a 4. Thank you. Okay, so up until now, we've just said cannot be simplified or does not have a real answer. But can we give meaning to the square root of a negative number? So the answer is yes. Mathematicians have created a whole nother number system called the complex number system. And these complex numbers allow us to work with the square root of a negative number. And complex numbers are used in many fields like engineering. They're used to find quantities involved in electricity. And in medicine, they're used in the calculation of blood in the bloodstream, flow of blood in the bloodstream. So before we discuss what the square root of negative 4 is, let's just think about the square root of negative 1. We'll make this a little bit simpler. The question of how to define the square root of negative 1 arose in the 16th century. Some Italian mathematicians were trying to solve cubic equations. So we're working on quadratic equations, which has a power of 2. So cubic equations have a power of 3 on the x. And their efforts led to the invention of a whole new class of numbers, beginning with this definition. We are going to say that the square root of negative 1 is this number called I. Okay, just to denote it with a lowercase I. We're saying, well, it's got to be something. I need to call it something. Let's call it I. New symbol, new kind of number. And now we can find the square root of any negative number using our product rule that we learned a few lessons back. So if I want to take the square root of negative 4, I could rewrite that as the square root of negative 1 times positive 4, right? Because negative 4 does equal negative 1 times 4. So I replace the negative 4 with negative 1 times 4. And then I can take two separate square roots. Square root of negative 1 times the square root of 4. The square root of negative 1, I just told you, its definition is I. So this is I times square root of 4 is 2. I times 2, or 2I. So let's do another one, the square root of negative 49. Rewrite negative 49 as negative 1 times 49. Take the square root of each number separately. The square root of negative 1 times the square root of 49. Square root of negative 1 is I. Square root of 49 is 7. I times 7, we typically write as 7I. It's just, you can leave it as I times 7. It's just a common practice to put the letter second. All right, one more where our number's not a perfect square, the square root of negative 12. So I'm going to rewrite this as the square root of negative 1 times 12, which is the square root of negative 1 times the square root of 12, which is I times the square root of 12. But square root of 12 is not completely simplified, right? it's not a perfect square number, but it does have a perfect square factor, which is what? 4. So I can rewrite square root of 12, copying the I, as square root of 4 times 3. And then this is I, square root of 4, square root of 3, which is square root of 4 is 2. So I have 2I square root 3. So in general, if you want to take the square root of a negative number, it's I times the square root of the positive. A plus BI, numbers that look like A plus BI, so a regular old number plus an imaginary number, are called complex numbers. I is an imaginary number, by the way. I didn't say that word before. I is called an imaginary number. So if you have a real number plus an imaginary number, we call that a complex number. And if B is 0, that means that the whole imaginary part goes away. We just get a real number. So all real numbers are automatically complex numbers. They don't. You mean on the XY plane? They don't. Yeah, you can't see them. Because the XY plane is a real number line for X and a real number line for Y. So it's reals and reals. There's no, it's like another dimension. Yeah. All right, so if I want to finish the equation I was trying to solve before, I was trying to find the zeros, and I stopped when I saw that negative under the square root. Now I can replace that square root of negative 4 with a 2i, right? I now know that the square root of negative 4 is 2i. So this is 4 plus or minus 2i over 2. Break it into two fractions. So this is 4 over 2 plus or minus 2i over 2. 4 over 2 is 2. 2i over 2 is just I. Okay, so my solutions are 2 plus or minus I. Those are complex numbers. Like we were just saying, you can't see them in the XY plane. That's why when I graphed that parabola, it doesn't ever cross the x-axis, right? Because the x-axis are solutions when that equation equals 0. But you can't see them because they're not real numbers. Okay, so you can't see them in that picture. Is there a way to figure out how many solutions and what kind of solutions a quadratic equation has without going through the entire quadratic formula calculation? So yeah, below each graph, we're going to see the nature of the solutions, right? How many and what kind they are. So just remember, a rational number is any number that can be written as a fraction, a ratio of two integers. And numbers with radicals in them are called irrational numbers. So for this graph, we have two rational solutions because it goes through two nice grid points, two rational solutions. For graph B here, it just touches in one spot, one rational solution. Touches right at 2. 2 is a rational number, one rational solution. For graph C, we have two irrational solutions. We solved this last class, and it turned out that the solutions had radicals in them, so those were irrational. And for graph D, we have two complex, that is, imaginary solutions. Okay, so if you have a quadratic equation, ax squared plus bx plus c equals 0, a special quantity called the discriminant, which is b squared minus 4ac, can tell us about the nature of the solutions. Where have you seen b squared minus 4ac before? It's in the quadratic formula. It's the part that's under the radical, it's the part that's under the square root. All right, so for each of my 4 graphs that we were just looking at before, I want to calculate the discriminant and then list the kinds of solutions we get, right? So I already have the kinds of solutions listed. So A was 2 rational, B was 1 rational, C was 2 irrational, and C was no real. All right, well, it was 2 complex zeros. Okay. All right, so now I'm going to calculate the discriminants. B squared minus 4AC. I don't need the square root at all. That in the quadratic formula, that part is under a square root, but I don't care about that. Okay, so B here is 5, so this is going to be 5 squared minus 4 times A times C. So it's 25 plus 24, which is 49. Okay, in my next one, B is negative 4 minus 4 times A times C. So that's 16 minus 16, which is 0. Am I losing you guys? No? Okay. All right, here I have B squared, 2 squared minus 4 times A times C. So that's 4 plus, because it's a negative times a negative, 4 plus 20, which is 24. And then one more, negative 4 squared minus 4 times A times C. So that's 16 minus 20, which is negative 4. Okay, so what's special about the number 49? It's a perfect square, yeah. So that's what makes us, that's what makes this happy 2 rational solutions happen, right? Yeah, whenever there's a perfect square as the discriminant, you get 2 rationals. It's on the next page. Yeah. The number 0 is special all by itself, right? The number 0 is the numbers between positives and negatives, right? And whenever you get a discriminant that's 0, you get 1 rational solution. Right? So this is perfect square 0. Now 24, it's positive, but is it a perfect square? No. So that leads to irrational solutions. If the number under the square root in the quadratic formula isn't a perfect square, it means you're going to end up with a radical in your answer, which means you're going to have 2 irrational solutions. So this is non-perfect square. Has to be positive, yep. You'll end up with a radical, giving you 2 irrational solutions. And then negative 4, that's special because it's negative. Right? The fact that that's, whenever you get a negative as the thing under the square root, you're going to have complex solutions. You're going to have i's. So as a little summary, right, the next page, yeah, it will never hit the x-axis if it has complex zeros. Yep. So our conclusions are the discriminant, b squared minus 4ac. If it's 0, there's 1 rational solution. If it's negative, there are 2 complex solutions. If it's positive and a perfect square, 2 rational solutions. If it's positive but not a perfect square, 2 irrational solutions. All right, so I'm going to do one of these with you. One example where we talk about the discriminant, the nature of the solutions, and the solutions themselves. Okay, so my discriminant is always b squared minus 4ac. So in this case, that would be 25, or 5 squared minus 4 times 2 times negative 2. Okay, so that's 25. Negative 4 times 2 times negative 2 is positive 16. 25 plus 16 is 41. It's positive, right? Is it a perfect square? No. So I'm going to have two irrational solutions. Two irrational solutions. And then if I want to find the actual solutions, I have to use the whole quadratic formula. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. I can save myself a little work here because I already know what b squared minus 4ac is. It's 41. So this is going to become negative 5 plus or minus the square root of 41 all over 2 times 2. And I'll just write that as a 4. Nope, because a is positive 2. Yep. 41 is not a perfect square. Does it have any perfect square factors? No. Yeah, no perfect square factors, so I'm actually done, right? I could circle that, or if I wanted to, I could break it into two fractions, negative 5/4 plus or minus radical 41 over 4. So this or this would be acceptable answers. Now let's see, did they tell me to round it all? Nope, leave your answers in reduced radical form. So no calculators necessary in this part. Okay, so I'm going to leave you to some more practice using the discriminant to determine what your solutions are going to look like, and then actually finding the solutions.